So decoding. Topics covered: the decoding algorithm and the properties of convolutional codes. The last two sections we'll be covering in Chapter 7. So we saw here the block diagram. We're looking now at the convolutional decoder. How is it that we take this information that was transmitted during the additive white Gaussian noise channel? Some bits in the code words were flipped, and I have to figure out from there how to correct the errors. The first part is here, where I do the demodulation and I feed information to the convolution decoder. First part to discuss is at that link there, because we have two choices. We could do what is called hard decisions, or we can transfer what are called soft decisions. So I go from modulation, from this box, demodulate, into the box which says decode. And in this transition, what kind of information am I transferring from the demodulator to the decoder? Hard decisions means that the decisions come from a finite set. In the terms of binary, it's either a zero, logical 0 or logical 1. Or if it's BPSK I was using, it's -1 or +1. There's no information about how confident I am in that decision. The demodulator says, I compare it to my threshold, and it's positive, so I think it's logical 1, or it's negative, I think it's logical 0, and it just gives the result. Soft decisions are different. Soft decisions come from a continuity. It can be any values. So even though it's binary data, the soft decision could be something like 0.3 or -0.9. And now we're keeping information from the demodulation part about how much confidence they have in the decision. So a couple things. First of all, which one is going to have better performance? Well, soft decisions are going to have better performance for sure, because it's not just the decision itself, but information about the confidence in the decision. Yeah, sure, this is better. Which one is going to be more complex? Oh, soft decisions are going to be more complex. I can't just work on a finite set of values. I have to start working on continuous ones. So this is more complex, but higher performance. So we're going to stick in this Chapter 7 to examples from hard decisions. And we'll talk a little bit about soft decisions and maybe see some examples later on. But both exist. So let's look at this idea of hard and soft decisions. If I look at the binary transitions, for instance, if I do a hard decision, then basically at the intersection of the two conditional probabilities, here's the probability of the received signal based on a 1 being transmitted. So here's the average value for a 1. And then there's the variance, which is determined by the noise level. Here is the conditional probability if the second symbol, in this case a logical 0, is transmitted. And in that case, here's the mean. And where these two intersect, that becomes my threshold. And if my received signal is to the right, I will send a 1 to the decoder. If it's to the left, I'll send a 0. Now let's suppose that instead I'm doing soft decisions. Well, it's a soft decision, but I'm still going to quantize the soft decision. So for instance, I can get a 3-bit quantization of the soft decision. That means that I'm going to divide the received signal, instead of even the 0.3 and the 0.9, I'm going to give you 3 bits that tells you which bin it fell in. And the closest bins with the most noise will be these two. And as we get over, that will represent less likely states where there were larger amounts of noise. But in any case, I'm mentioning this because when you read about soft decision decoders, they will generally specify the number of bits of resolution in the soft decision. And you'll find that 3-bit soft decision is usually more than adequate to get the advantage of soft versus hard decision. So you don't want to increase the complexity too much, and there's no point in making it truly continuous, all values, that you can quantize it and still get virtually all the improvement you would get in moving from a hard to a soft decision. Because we have two kinds of information which are transmitted from the demodulator into the decoder, that means that the decoder has two different kinds of metrics that it's going to be using, depending on whether it's dealing with hard decisions or whether it's dealing in soft decisions. As I said, we're going to be looking at hard decisions, And when we work with hard decisions, we're going to be talking about the Hamming distance between a received word and the code word that it might have been. So this code word that has no errors in it, there are only a few code words which are allowed by the code. And this is the received vector, and of course things could have been flipped by noise. So we want to see how close is what we received to each one of the possible code words, for instance. Hamming distance, what does that mean? Well, in the Hamming distance, the code word is binary, and I got hard decisions, so this is binary also. And so if I'm looking at a sequence, the distance between the two sequences is just the number of bits which are different. Now, Euclidean distance is what I use in the case of continuous decisions. So this is for soft decisions, and now I have a sequence, and you can think of them as like, I would say IQ coordinates, but let's say we're doing binary. So I have this line. Here's 0. Here's 1. Let's say it's BPSK, it's just easier. Here's my threshold. And if the hard, it would be like one or the other. Here, it's actually some point here on the real line that it's represented. It could be in the IQ plane if it wasn't binary, so we give a nice general equation here, which could be used also for a two-dimensional representation of the symbol. But in any case, for soft decisions, what I do is I use something called the Euclidean distance. And the Euclidean distance between these two is I take the distance between the true one and the, for instance, if this was what was received, this would be the distance between the received signal and the potential correct word. And then we would square that, and we would do the sum of the squares of all the differences, and then we would take the square root, and that would be the Euclidean distance. So, two metrics. We can see why this would be more complex to calculate, and this is the reason that the soft decision is more complex. And this is much easier to implement. If we want to look back into the probabilistic framework that we built for channels for additive white Gaussian noise, if we're looking at hard decisions, it's like taking this idea of the received signal being the transmitted signal plus noise, that idea, and that this is Gaussian. Instead, what I'm doing is I've already made the decision, I quantized this after I compared it to a threshold, and in that case, this whole representation could be based on let P be the probability that I mistake a 0 for a 1. So 1 was sent, but I think it's a 0. And I'll assume that this is equal to the same probability that 1 was, I pick a 1 even though it's 0. So two types of errors, assume the two types of errors have the same probability, which I call P. So this would be what we call a binary symmetric channel. So there's 0 or 1 is a possibility of what's transmitted. There's a certain probability that I will make a mistake. I call that P. And of course, if I don't, the opposite would be the probability I don't make a mistake. That's 1 minus P. And so this would be, I would just come up with the probability of error. And once I've determined the probability of error, then I just represent the whole channel by this simple transition of a binary symmetric channel. So it just takes it from here for a given bit error rate, a different specific signal to noise ratio. I get a bit error rate, and then that just comes in here, and that represents what's going on for my performance with the encoder. So when we do our decoding, as I mentioned, we are going to exploit correlations, redundancy, which were introduced between our code words. Okay? So the decoder has to exploit the correlation. So we start with this data, which is modeled as being completely independent. One data bit from the next, I don't know what's coming. And I put it through an encoder. The encoder introduces correlation, right? That U1, it depends on what 1, 2, and 3 are in the register. So there's a dependency that is introduced. And the decoder exploits this dependency, this correlation, which becomes the structure in the trellis. And essentially, when we look for a maximum likelihood detection in such a situation, we're actually looking for a maximum likelihood sequence estimation. So as I mentioned earlier about we're going to look for a path describes a sequence. So when we're doing our detection, we are essentially doing what's called maximum likelihood sequence estimation. And there's a very effective algorithm for finding the maximum likelihood sequence estimate, and that is called the Viterbi algorithm, and that's what we'll be describing for our decoder. So let's see how the decoder operates. What are the operations it performs in order to do the decoding? It will determine what are called branch metrics. Branch metrics, this is a branch. I go from B to C, this transition, and that branch is going to have associated with it a certain feeling, let's just call it that, for how likely an error was to have occurred here or not. These are called branch metrics. So everywhere in our trellis, we're going to be assigning values to all of these transitions. And these transitions are going to be based on what it is we actually received. So this is the encoder structure. This encoder structure is based on, these code words and this code, this collection of coded outputs determine which encoder I was using, and therefore this encoder corresponds to the one we saw in the example previously. And the previous example I put through this sequence of data through this trellis. We saw that go on. What I want to point out now is that when we use our decoder, we're also going to use a trellis. For sure we're using a trellis. So we're going to take the same structure and we're going to repeat it, only this time the decoding is going to be based on what the received vector is. So Z is the received vector. I should write this over here. M is the transmitted message. U is the coded transmission, and Z is the noise corrupted received signal. So the encoder takes M. The encoder takes M and gives you U, and then U is transmitted. That's the job of the transcoder. Now in the decoder, I start out with Z, which is the noisy contributions. And here is going to be what is received at the receiver, and we will introduce some bit that was flipped as it went through the transmission process. And so now we're going to discuss how can a decoder come up with the best sequence, the most likelihood sequence of bits that was transmitted. And we'll see that in order to do that, we're going to create these branch metrics, which are going to be written next to these valid transitions. So in the encoder, the valid transitions contain code words. And in the decoder, the valid transitions will now have a branch metric that we'll be calculating. So how do we calculate what that branch metric is? Well, I need the encoder in order to build the decoder. So let's say that what I receive in some time interval, and remember one of these tiles here is a time interval. Suppose I receive a 1-1, and I'm assuming that I start at state A, because I know that all transmissions start from state A. I look up at my encoder, and I say, well, the transition from A to A should put out a code word of 0, 0. What I received was 1-1. So that means that if the transmitter really sent 0, 0, and the receiver got a 1-1, that meant that there were 2 bit errors. Both of those bits got flipped. So the branch metric that I'm calculating is the Hamming distance. How far is 0, 0 from 1-1? Hamming distance is the number of bits that are different. There's 2 bits that are different. So next to this transition A to A, I write 2. Because if there really was a transmission that led to a transition from A to A, that meant that there were 2 errors during that transmission. Now I look at the other possibility. When I go to A, from A, I could have gone to B, and I look in B and I say, well, the distance between what was received and the code that would have happened on this transition is 0. Okay, so then there would be like 0. And then you can ask, is it more probable to get no bit errors or to get 2-bit errors? Okay, so you know that the probability of bit error certainly better be less than a half. If I'm in a channel where more than half the bits are getting flipped, I should not be transmitting signal, or, well, whatever. You can always count on the system having a probability of error that's less than a half. So that means that the probability of no errors is a lot more probable than the probability of 2-bit errors, or 1-bit error, but certainly 2-bit errors, like big difference. Okay, but we're not going to do that, all right? That would be like making no sequence, just picking which one is it. So we're not going to do just that, but we're going to keep going. So we have a lot more of our trellis to exploit. But the important thing I want you to get from this exercise is just how do I build my decoder trellis? So this is the way we build a decoder trellis. We take, during a time interval, what was the received sequence? So this is our hard decisions we got from our demodulator. And for each one of the transitions that are available in that time slot, now I've got 4 transitions in this time slot. Because I know I started at A, but now I could be at A or B. So I have 4 branch metrics that I have to calculate. So I take the difference, 0, 1, and now I have 4 values here in the encoder, and I step through each one of them, and I calculate what is the Hamming distance between what was truly received and what might have been transmitted. And so now I have 1, 1, 2, 0 as the transition possibilities, the branch metric in that transition. Of course, I get to the next one, and now I'm in sort of steady state. Now there are a total of 8 transitions which are possible. And as I go forward, there will always be these 8 transitions which are possible. So in this case, I have 0, 1 as the received code word. And I look at the valid code words, these 8 valid code words, and I calculate the distance between the code word received, corrupted, noise-corrupted code word, and I calculate the distance, the Hamming distance between each of them. So, having filled up my decoder, this is just like step 1. Just go through and fill it up with all of this. This is my output from my demodulator. What does my trellis look like, my decoder trellis? How am I going to use this decoder trellis to actually decode the signal? Now, to understand that, we have to move from branch metrics to path metrics. So here we had branch metrics. So I need to find now, instead of a branch metric, now I'm looking for something called a path metric. A path metric is going to be a function of all of the branch metrics along a path. So let's look at just 2 paths possible that I trace through my trellis. These are valid transitions because they follow the lines that I've established before. And I have, going to a certain point at the 5th time interval, if I'm at state A. Suppose I'm at state A, there are 2 possibilities of how I got to state A at time 5 that I happen to draw here. In this case, there's 2. And each one of these paths has a different history behind it. So the transition that's dotted is a 1. Transition that's solid is a 0. So if I look at the upper path, that would be a 1, a 0, 0, 0. If I look at the bottom path, that would be if I had transmitted a 1, a 0, 0. Okay, so 2 potential solutions. Solutions of what was transmitted, a sequence of what could have been transmitted, is represented by a path in the trellis. And each one of these paths has a path metric assigned to it. And the path metric is just the sum of the branch metrics. So in this case, I said it was a 1, 0, 0. And I've taken my decoder and I look at, along those transitions, what were each one of the branch metrics, and I add them up. So I get, there was a 0, there was 2, 1, 1. That gives me a branch metric of 4 for this path. Okay, so I have a path metric for the 4. Now I do the same calculation for this other path. And again, this path corresponds to a 1, 1, 0, 0. That would have been my choice. And on this path, I add up all of the branch metrics, and the path metric I get is a 1. So if I followed the path up here, I call this the upper path and the lower path. This one comes in from the upside. If I do that, I would have gotten a path metric of 4, and if I do the other path, I would have a path metric of 1. So what does that mean in terms of Hamming distance? I could have had 4-bit errors, or I could have had 1-bit error. And I ask myself, which is more probable? Which is more likely? Is it more likely that I had 4 errors, or is it more likely I had 1 error? Well, 1 is smaller than 4, and in a channel p less than 0, that would be more likely. So the bottom path is the more likely path of the two paths. So there's only 2 ways I can get to state A. I could have come from state B, or I could have C, or I could have come from state A. That's the only way to get to state A, coming from A or coming from C. And in these 2 examples, where there's 2 possibilities are traced back with 2 different lengths, what I do is I pick one of them to survive. Although there are always 2 possible paths to go to any one point, I don't allow myself to keep 2 paths. I force myself to pick one which is better than the other. And the way I pick it is based on the path metric. And I call the one that I keep the surviving path. So in this case, the lower path is going to be the surviving path. And the other path I'm going to eliminate. And so this idea of choosing path is how the Viterbi algorithm is able to be a computationally and memory efficient way of finding the most likely path through a trellis. And the best way to see how this algorithm works is to actually step through it.